Okay, class 12, this is the second part of the video on drift velocity. Okay, so if you check the first video, all right, we've seen that when a conductor is subjected to an external electric field or potential difference, okay, then the electrons, they experience a force due to this electric field, okay, due to which the electron starts accelerating. Okay, so we've seen that the expression for the acceleration is given by this E, capital E by m, where m is the mass of the electron, small e of course is a charge, E is the external electric field. Okay, and we saw that the drift velocity is given by a tau, where a is the acceleration, a tau is something called the relaxation time. Okay, so substituting for a from this equation, we see that the drift velocity is given by minus E, capital E by m into tau. Okay, which can also be rewritten as drift velocity is minus ev by ml into tau, since E is v by l. Okay, so starting from this equation, equation 3, we see that Vd is this. Okay, now rearranging the terms, Vd is E tau by m into minus E. All right, now this thing E tau, small e tau by m, is rewritten as mu e now, where mu e is something called the mobility of the electrons, where mu e is given by E tau by m. Okay, this mu e is called the mobility of electrons. Remember, now what is mobility? Mobility is simply the ability, of course, that are free electrons to move under the influence of an electric field. How fast the electrons or how slow the electrons are moving inside a conductor. Okay, the measure of that is what is called mobility. Okay, the faster the electrons are moving inside the conductor, the more the mobility, of course. The lesser the speed of the electrons, okay, the lesser the mobility. Now, mobility depends on two things. One is mobility depends on the temperature. Okay, you can see from this expression, mu e, the mobility is E tau by m. Now, E is a constant, m is a constant. Okay, mass of the electron is a constant, charge of the electron is a constant. So, it basically is dependent on the relaxation time. Now, remember, for a given conductor, at a given temperature, at a constant temperature, the relaxation time is a constant for that conductor, remember. Okay, for different conductors, the relaxation time will be different, and at different temperatures, the relaxation time will be different. Okay, so therefore, remember, we are saying mobility depends on the temperature, because once the temperature changes, the relaxation time also changes. Okay, so the mobility also changes, remember. And the next thing is, I have already mentioned, mobility depends on the nature of the material. For different substances, for different conductors, the relaxation time is different. Okay, so therefore the mobility also changes for different substances. So therefore mobility depends on two things. Mobility depends on the temperature, and mobility depends on the nature of the material. All right, okay, so from this expression, Vd is minus mu e, mobility into the electric field. We can also write mobility is Vd upon E. Okay, all right. So from here also we can give a quantitative definition of mobility. We can say mobility is the ratio of the drift velocity to the electric field. Mobility is the ratio of the drift velocity to the electric field. Okay, if you are asked the definition of mobility, you can write that too. Okay, so from this expression and from this expression, see what the units of mobility are. Okay, check what the units are, and also check the dimension of mobility. Okay, see, relaxation time is, let me tell you this. Okay, from here you get another unit, check that. Let me tell you this. E is a charge which is measured in coulombs. Relaxation time is in seconds, and mass in kilograms. So one of the units of mobility is coulomb second per kilogram. Okay, that is one unit. Also check the dimension of mobility. All right, so the other thing that I want to discuss in this video is relation between electric current I and the drift velocity Vd. Okay, now this is something very, very important for you all. This derivation might come. Okay, in the previous video, okay, we've done the derivation for drift velocity. I don't think you'll get the expression to derive the expression for drift velocity. These different expressions for drift velocity, I don't think you'll get a question to derive these expressions. All right, what you might get is, you might get this. Okay, relation between electric current and drift velocity. Now, when I say you don't get the derivation to derive, Okay, but do remember these expressions. Okay, you might need these in numericals. Okay, so remember these relations, especially the relations you might need it in while solving the numericals. But this derivation is very, very important for you all. Remember, that is the relation between electric current and drift velocity. Okay, so say for example we have a conductor, we have a wire, okay, a magnified picture, a 3D picture, this is, don't forget. All right, so this is a wire. Okay, wires are basically cylindrical, so this is a wire. Now inside this wire, of course, we have free electrons, and I have chosen two cross sections here. One is this and the other is this. This is 1, this is 2. All right, now what we want to see is, we want to see how much is the current flowing through this conductor in a certain time. Whatever we want to see, what is the current flowing through this conductor, through this wire in a certain time. Okay, so let us suppose some things first. So small n, this is n, not m. Okay, this is n. N is the number of electrons per unit volume. Okay, now in the previous video, if you have checked that previous video, I have written capital N over there. Okay, capital N was the total number of electrons inside the conductor. Total number of electrons in a conductor. All right, capital N was the total number of electrons in the conductor. But see, this is completely different from that. Remember, this is the number of electrons per unit volume. Okay, so if say for example this is a unit volume, say for example, so what is the number of electrons in this unit volume of the conductor? It's N. All right, so what is the total number of electrons in this conductor? If the total volume of the conductor is V, then capital N, the total number of electrons in the conductor, will be small into capital V. This is it. Remember, don't forget. So the number of electrons per unit volume means the total number divided by the total volume of the conductor. Don't forget that. So small n is the number of electrons per unit volume. Capital A is the cross-sectional area. So the cross-sectional area of this thing, of cross section 1 is A, cross-sectional area of cross section 2 is A. Okay, so what we want to see is, let us suppose a certain time t. Okay, now we want to see what is the current flowing through this conductor. Now in order to get that, what we want to see is, we want to find out what is the total, since current is the rate of flow of charge. If we can we can find out what is the total number of charge flowing, say for example through this cross section. Let us look at cross section 2. So if we can find what is the total number of charge flowing through this cross section 2, okay, in time t, all right, then we can find the current, because current basically is charge divided by time. So if we can find what is the charge flowing through this cross section in time t, then we can find current. All right, okay, so if Vd is the drift velocity of the electrons, then in time t, okay, the electrons are going to travel a distance Vdt. In time t, distance traveled by the electrons is Vdt. Okay, now let us show that Vdt is this distance. Say for example, let us assume that Vdt is this distance. All right, so in time t, the distance that the electrons are traveling is this much. Okay, understand this very, very clearly. Okay, it's very, very important for you to understand this. So in time t, the distance traveled by the electrons is Vdt from cross section 1 to cross section 2. So in time t, the electrons that are here, okay, will also reach the cross section 2 here. So to say, they cross this cross section 2. Okay, and of course, if these electrons are reaching cross section 2 by traveling this amount of distance in time t, the electrons in between 1 and 2, all of the electrons in between 1 and 2 will obviously cross this shaded region, this shaded area. Okay, all of the electrons in between 1 and 2, all of these electrons are going to cross our cross section 2, our area 2 in time t. All right, so so what the case is like is, all of the electrons in the region between 1 and 2, since they are going to cross cross section 2. So therefore number of electrons passing the cross section 2 or the shaded area, okay, in time t, okay, number of electrons, let us call that q, will be the number of electrons into charge of the electron. This is the charge. This let me not write electrons, let me write charge here. Okay, total charge or the number of charge passing through cross section 2 in time t, let us call that q, is the number of electrons. What is the number of electrons? How many electrons are there in between 1 and 2 now? In between a region, in between areas 1 and 2, how many electrons are there? All right, now we know in a unit volume the number of electrons is n. All right, so if we can find what this volume is, now what is this volume? This volume is the length VDT multiplied by this area. Okay, the volume between 1 and 2, understand this clearly, volume between 1 and 2 is equal to the distance length VDT multiplied by the area, because volume is area into length. Okay, so that is exactly what I've written. So this part here, VDT into A is the volume of this space, is the volume of this space, the thing that I've written inside the bracket. VDT into A is this volume. All right, now if n, now since n is the number of electrons in a unit volume, the number of electrons in this volume VDT into A will be n into VDT into A. So what is this part? Okay, this thing inside the square bracket, n into VDT into A is the total number of electrons, okay, in between 1 and 2 in this space. Okay, mind you, this is a 3D picture. Okay, so this is the number of electrons. Now what is the charge of the electron? The charge of the electron is E. Okay, so understand this part very, very clearly. So number of charge passing through the cross section 2 in time t is q, which is n into VDT into A into E. Okay, so therefore q is NEA VDT. Now once you understand this part, okay, so this is the charge flowing through cross section 2, okay, in time t, all right. So what is electric? So once we found this, calculating the current is not a big deal. So current, electric current flowing, I will be q by t, which is NEA VDT into t, divided by t. So therefore current is NEA VD. So this is a very, very important relation. Okay, if you don't understand, this part, okay, how we calculate this, do let me know. All right, do let me know. So the current is NEA VD, a very, very important derivation for you all. Okay, all right. I hope you all are making notes while watching the video. Okay, do so, class 12. Okay, this thing is very, very important for you. All right, so stay safe. Thank you.